Hello, my beautiful computer science students. Welcome to our third lesson in Unit 10, where we are going to go over a classic recursion problem called the Tower of Hanoi. So this is a kind of a problem solving exercise for you. So I've told you that you won't have to write recursive code on the AP exam, but I did want to show you an example of where recursion can help us easily solve a problem that would be difficult to solve any other way, right? And that's kind of why the Tower of Hanoi is like the pinnacle recursive example that most people get into when they first start writing recursive code. So I want to propose the problem and exactly what it is. I want you're going to try the problem and you're going to try to find the solution on your own. And then we're going to get into the code and why the recursive solution is the best solution here. Okay, so that's what we're going to do with this problem. So here's the problem setup. Okay, so you're going to have a tower of what's called disks. You are going to move this tower of disks from one tower to another tower. And so if you look at the screen, I have this visual. Visuals are going to be key here for this problem. So the problem setup, I have three distinct disks. So no two sizes are the same, and I've labeled them 1, 2, and 3. And they are all in one tower. I'm calling Tower A. Now your goal is to move all of them to Tower B. Okay, so you're starting in Tower A and you're going to move them all into Tower B so that they stack in order. Okay, so that's why I'm flipping between the two here, A to B. You're moving them all. Now there are some rules when you're moving them. Okay, so here are the problem rules and the problem specifications. So that there are n disks labeled 1, 2, 3 all the way up to n. We're going to start with 3 disks, as you see here on the screen, and we're going to make our way up to larger values of n. So there's however many disks, we're going to start with 3. There's always 3 towers that we're going to label A, B, and C here. There's always 3 towers. No disk can be on top of a smaller disk at any time. Okay, so if I move disk 1 over to Tower B, and I can't move 2 on top of it. This is not allowed, okay? So I can't have a bigger disk on top of a smaller disk when I move it, okay? That is not allowed. All the disks are initially placed in order on Tower A, so 1, 2, 3 at the bottom, and you're only allowed to move 1 at a time, and it must be the smallest disk on a tower. So I want to move all of the disks from A to B. Tower C is just kind of a utility tower. I can use it to help me accomplish my goal. Now when I move a disk, again, I can only move 1 at a time, and it has to be the smallest disk on the tower. So from Tower A, my only option is to move disk 1. I cannot move like disk 2 here. I can't move this. Okay, this would not be allowed. And the visual I like bringing in class is this toy. Okay, so if you see on the screen this toy, a classic children's toy, and one that I readily have available. So I have my 3 disks right here, okay, all of different sizes, and you can see the different colors. And they're starting all off on Tower A. Okay, now my goal is to move them all to Tower B. Okay, but I can only move 1 disk at a time. And it has to be the top disk or the smallest disk. Like I can't move, you can see I physically can't move this disk 3 here. I can only move the top disk, and I can't put it on a bigger one. This wouldn't be allowed. So my only option would be to put it here. Okay, does that make sense? That is my conundrum. That's the problem that I am trying to solve. And I want you to try it first. So I have this. If you have this, that is amazing that you have this, but probably something that you have more readily available would be change. So if you go grab a quarter, nickel, and a dime, those can represent your 3 disks. Okay, and you're going to start with them on Tower A, so just like a position on your desk, right? So Tower A, and your goal is to move them all to Tower B in that same order, but you can only move one disk at a time. No disk can be on top of a smaller disk, and the disks can only be moved with the smaller one first. Okay, so go ahead and pause this video and try it. Okay, try this 3-disk solution. Okay, and when you come back, I'm going to show you what the solution is. Okay. All right, hopefully you paused it and hopefully you tried it. If you did not, well, that's just what it is. What's the 3-disk solution here? I'm going to start here. So I move 1 over to B, and I move 2 over to C. Okay, so I get them spread out. From here, then I move 1 on top of 2, and I move 3, my base, over to B. I move 1 over, 2 over, and then 3 over. That is my 3-disk solution. Okay, so that was pretty straightforward, and I do have a lot of students who get that eventually. It might take you longer than others, and that's fine. But for the most part, you can kind of figure that out, right? That's your solution. Now let's try a 4-disk. Okay, this is where it gets interesting, right? So on my example, I'm going to add a red one on top. So 4-disk solution. You can add a penny in here, and you're going to try to move all 4. Again, the goal is A to B. All the same rules apply, but now you just have 4 disks, right? So I can move this here. I can move this here. My only option is to move this here, right? Okay, I'm going to try not to, because I know the solution, so I'm going to stop there. But your goal is to move all 4 of these right here. Okay, all 4 of these right here. So again, pause it and see if you can figure it out on your own first, and I'm going to show you what the solution is when you're ready. Okay. Hopefully you're ready now. It's so weird when I say pause the video, but I don't pause, I keep going. So 4-disk solution, this is what it looks like. Okay, you're going to move 1 over and 2 over, and then 1. Then you're going to move 3 over, and then 1, 2, 1. Now, I want to pause here because I want to point out what we just did was the 3-disk solution, right? That was just the 3-disk solution, the same maneuvers that we just did. And that's going to be an important part of the recursion that we are building, right? So recursion calls on itself. So one of our, not necessarily our base case, but one of the ending cases is a 3-disk solution. Okay? So keep that in mind. So now we got to keep moving. 1, 2, over to 1, move the 3 over, 1, 2, and move the 1 over. Okay, so again, that same maneuver, now we changed up the towers that we moved it between, but that same maneuver, starting with the stack of 3, moving it 1 over here, over, moving 1, you can't see me, I forgot, but moving it over, moving the stack of 3 was the same. We just changed the towers that we did it with. Okay, so moving that stack of 3, that's going to be key to building our recursive solution here. Then I move over 4. Okay, because B, I want all of them to end up on B. All right, so now that it's over there, now I'm going to go through that same series of moving my 3-disk solution. I move 1, 2, 1, move the 3, move 1, 2, 1. And I have my solution. Crazy, right? Now, when you were trying with your coins, chances are you were doing some trial and error, right? Which is, of course, normal. You're problem solving. You're trying to figure it out, through trial and error a lot of the times until you get a solution and until you know the solution. We're going to talk about how we can solve this recursively, and I've already tried to talk about how it can build that recursion back to that 3-disk solution. So 3 disks was okay to find pretty manually, easily found manually. 4 discs is kind of tough, but maybe some of you were able to figure it out. I love that. Once you get into 5, 6, 7, however many discs, it does become harder to solve. Unless you remember that recursive solution, right? I always compare it to like a Rubik's Cube. Okay? If you don't know the algorithm for a Rubik's Cube, it feels impossible to solve just by trial and error, right? But if you know the algorithm for the Rubik's Cube, you can solve that in less than a minute, okay? It's the same with this Tower of Hanoi problem, okay? If you don't know the recursive solution, if you're just trying to do it like with 5, 6, or 7 discs, it's going to take you a while to try to manually figure out how to do it. But if you know the recursion behind the Tower of Hanoi, you're going to do it so much quicker. Okay, so that's what I'm trying to show you with this problem. So we're going to generalize how we're moving these disks into basically 3 positions, okay, because there's going to be 3 main lines of code in our recursive solution. Okay, so this is our original position. Okay, right? There's n number of disks, however many there are. Position 1 is moving all of the top disks from A to tower C recursively. Okay, and we're going to talk about how we move recursively in a moment. But 3 positions. Position 1, our first step is to move this chunk, these top chunks, over to tower C. Position 2 is just one step, moving this over here. Okay, whatever your base one is over to B. That's just one step. That's no recursion, that's just one step. Position 3 is moving all of these from C to B, again, in a recursive fashion. Okay, and that's what we're going to do recursively. Now, since I know how to move recursively, I can very quickly solve for 5, 6, 7. I can quickly do that. I won't because I don't want to show off, right? No, I won't do that. But I can do it quickly because I know the recursive solution. Not that I've memorized every step, but just because I know how to move recursively. Okay? So how do we move recursively? Okay, how do we move recursively? Let's start building this idea of code here. So I have 5 disks, let's say, starting in tower A. It's called my from tower, to tower, and other tower. That's what I call them in the code that I have written that we'll get to in a moment. But I have from tower, to tower, other tower. So what I'm going to do is move my top 4 disks from my A to my C. Okay, so how am I going to do that? I'm going to call them by their numbers, 1, 2, 3, and 4. So to move recursively, I move 1, 2, 1. Okay, that's almost like not my base case necessarily, but my recursive movement that I do most often. Okay, 1, 2, 1. Then I move 3 over. Then I move 1, 2, 1. Okay. Then I move 4 over. Then I move 1, 2, 1. Okay. Then I move 3 back over. Then I move 1, 2, 1. Okay. That was all position 1. And notice how I moved everything over to tower C. Okay. That's the recursive. Okay. 1, 2, 1, move move disk 3. 1, 2, 1, move disk 4. 1, 2, 1, move disk 3. 1, 2, 1, and you're back on tower C. Okay, that's your recursive pattern. Okay, so that's position 1. Position 2 is just moving the 5th block over. Okay, position 2 is just one line of code. That's it. Now we're moving into position 3, where we again move that disk 1 through 4 back onto tower B. So I'm going to move recursively. Here I go. I'm going to move 1, 2, 1. Then I move block 3. Then I move 1, 2, 1. Then I move block 4. Then I move 1, 2, 1, move block 3, move 1, 2, 1, and I'm done. Okay. Isn't that cool? Now, you won't be an expert in Tower of Hanoi off the bat, okay? That's fine. If you're a little, well, like, I kind of get it, but, like, that's fine. Okay, this is more just showing you that this problem is done in a recursive fashion, okay? So how do we code something like this? Well, we're going to do my favorite, pseudocode first, okay? So here's a little pseudocode for you. We're going to have 4 parameters. We have n being the number of disks. We have our from tower, to tower, and other tower. Okay, which our from tower was A, our to tower was B, and our other tower was C. Okay, but just to make it more general, from to other. Our base case is moving disk 1. Okay, our base case is moving disk 1. From wherever we're going from to whatever tower we're going to. Okay. Otherwise, I have my 3 positions, right? Position 1 was moving my n-1 disk from to the other tower, okay? And then that tower is just my my utility tower. Okay. Position 2 excuse me. Position 2, remember, was just one line of code. Position 2 wasn't a recursive. It was just the last disk from where I started to where I'm going, right? That was just one. And then the position 3 was a recursive movement, and it's the same movement just with different towers. I go from n-1 to from my other tower, my utility, to my to tower, and then my from tower is now my new utility. Okay, that's where it gets a little dicey from your A to your B to your C. But your tower positions are also coded recursively, right? Not just the n, whatever number you are moving. But that gets a little bit crazier. Here's the full code. Okay, not something you need to know by any means. Not something you need to even know how to write for the AP exam. Okay, so I don't want you to panic when you see this, but I do want you to see this because this full Tower of Hanoi code is not that much, okay, for what could be such a complicated problem. Okay, this is the solution for n equals 5 disks. Of course, n being however many disks you have, you could have 100. All right, and this is the code. It's going to print off what your movements should be. Okay, so this is a void method. It's just going to print off to the console what your movements. So basically, this code tells you, okay, you're going to move disk 1 from A to C, and then you're going to move disk 2 from A to B. Okay, so it gives you instructions essentially. You have your base case instruction. And then you have position 1 was your recursive call. Position 2 was just one movement, disk n from A to B. And then position 3 was a recursive call. Okay? So you have those 2 recursive calls in there. Okay? If you were to run this code for 5 disks, this is what will print off. It's the instructions for how you move. Okay? So this would be, okay, so it says move, and I have 4 disks here, but you get it. Move disk 1 from A to B. Move disk 2 from A to C. Move disk 1 from B to C. Okay? And notice that same pattern of 1, 2, move the 3. 1, 2, move the 4. 1, 2, move the 3. 1, 2, done. Okay? That pattern was how I said we move recursively. All right, and that all was position 1 code. Okay, meaning that was all code that happened before the position 2 call. Position 2 was just one line of code where you move disk n from A to B. And then position 3, again, notice the same pattern. 1, 2, 1, move disk 3. 1, 2, 1, move disk 4. 1, 2, 1, move disk 3, 1, 2, 1, and you are done. Okay. And then the ABC towers, coding this recursively gets a little bit crazier, and I don't want to go that deep into this Tower of Hanoi problem. This is just more an introduction into it. But you can also have the A, B, and C switch around recursively. And there is a pattern to it, kind of the same way that I have this pattern here that I'm trying to explain with the disk numbers. There's a pattern with the A, B, and C as well. But we'll leave that for another time. Okay. That's Tower of Hanoi. Yay! So exciting. Okay. So thank you for watching. Again, none of this is going to be on the AP exam. Okay. But I wanted to show you problems that can be solved with a recursive pattern and show you a little bit about how we write some of those recursive patterns and how easy it was to write a recursive solution for something that we really couldn't do with an iterative solution. So, but thank you guys so much for watching this lesson, and I will see you next time.